it is the second part of section 4.2, Hessian and principal curvatures. In the first part, we studied Newton's method. The function is defined on the d-dimensional space with a d large. Then its Hessian will be d by d metric and expensive to compute, and also its inverse will be non-trivial. So in reality, once you are using Newton's method, then you may try to use approximation of Hessian rather than using computing and using exact Hessian. Here in this part, second part, we'll try to understand the properties of Hessian and the role of the Hessian in Newton's method. Hessian describes the local curvature of a function. Hessian is a d by d metric, and we can find eigenvalues and eigenvectors. And here, the first principal eigenvector corresponding to the largest eigenvalue is the direction of greatest curvature. And last principal eigenvector corresponding to the smallest eigenvalue in modulus is the direction of least curvature. For example, in 2D, we may consider function given in this way. This contour plot, and center is the minimum. Then apparently this direction is now greatest curvature direction, so that one will be now U1 corresponding to the first eigenvector and also the largest eigenvalue, and that is now U2 and corresponding to the small eigenvalue. If dimension is larger than 2, then the corresponding eigenvalues are the respective amount of these curvatures. Okay. Eigenvectors of Hessian are called the principal directions, and the eigenvalues are called the principal curvatures. Okay, here let's see the observation. Let a Hessian metric be partially definite and its eigenvalue eigenvector pairs are given in this way. That means that here H U J is lambda j u j for j's from 1 to d. Now let's choose a vector from d-dimensional space. Then now it is partially definite, so that here by using the d eigenvectors, V can be expressed as a linear combination of the eigenvectors. So once you apply H inverse in front of V, then now we can get this one. Okay, from this one, we apply H inverse, then that is the same as U, J, and lambda J, H inverse Uj. Now divided by lambda J, then now H inverse, here Uj equals same as 1 over lambda J and Uj. That means that for H inverse, now 1 over lambda J and Uj are eigenvalue eigenpair. And here H inverse will be multiplied here Uj for each Uj. So H inverse uj is same as 1 over lambda j uj, so it is replaced in this way. And assume that here lambda 1 is the largest one in modulus, so that lambda 1 is the largest one, and then lambda 2 and so on, so that the smallest one is lambda t. Then among their reciprocals, 1 over lambda 1 is smallest. So in this expression, here u1 will be most diminished. That means that here, once eigenvalues are larger in this direction, then more diminished, and relatively the last one will be here not much reduced, so that the angle measured from H inverse V to the least principal direction of H, correspond to the smallest eigenvalue, becomes smaller than the angle measured from V. That means that here V is changing the direction after multiplication of H inverse toward the least principal direction. But this is true for the gradient vector. If you choose V from the gradient vector, then also it is true here. And we summarize here the inequality. Angle between the least principal direction and H inverse V is smaller than angle U sub t and V. And here, practically, we computed through this example. Now, I made here ellipsoid, and this is the minimum point. And at a point, I chose a point and measure minus gradient of f, then it is that direction. Now, also measure here the Hessian metric. Of course, for this case, it is 2 by 2 metric, and Hessian inverse is applied. Then, now it is changing the direction toward the least the smaller principal direction, and then in fact in this case is locating the minimum point. And we can summarize our observation here. The net effect of H inverse is to rotate and scale the gradient vector to face toward the minimizer by a certain degree, which may make the Newton's method converge much faster than the gradient descent method. Well, let's see this example. Here, this is now an ellipsoid, and minimum point is at H and K. Now, for any point at xy, if you are measuring gradient and the Hessian, and so that minus here the Hessian inverse and the gradient will be a vector such that the end point start from the xy, and now if you add this one to the point, then it will become now H and K here, okay? And all is facing toward the minimizer, and also in fact, okay, now from any point xy, and if you are adding this one, so the minus Hessian of f at xy, and inverse, and now gradient of f, of course here now xy, and then that is exactly the same as H and K. you can prove that. This is one exercise problem. You can prove it quite easily. Okay. Okay, that's the end of the section. Thank you.